Okay, now we are going to get into more details about what we are understanding from the semi-empirical and very simple potential functions. So, let us look at some of the non-bonded potential functions first, and the simplest one could be what we call as hard sphere. So, this essentially, if you look at in this, let me make it bigger. Okay, slide. So, if you look at this, sigma is giving you the lattice constant, and here what we are saying, if the particle comes here, it hits the hard wall. So, it is almost like spheres hitting the hard wall and bouncing off. So, this could be a very simple model where essentially at particular r, you essentially have a collision and you go away with the same kinetic energy that you came from. So, that becomes elastic collision. And the other one could be that there is a hard sphere, but there is a square well. So, we are again now looking into mathematical models that we are using for potential functions. So, in this case what will happen is that the particle is happy inside the square well, but when you heat the temperature, suddenly it moves out and then it is free to collide with everything else. So, this is a very soft potential in the sense it is a hard sphere inside a square well, but the amount of energy you take to get this particle out of this square well depends on the depth of the well. So, you can make it resistant or non-resistant against the temperature and the expansions and the pressure by changing the potential energy well. Now, if you look at the C, this shows a very simple Coulomb potential. It is a long range and it is good for the plasma. So, if there are gases which are completely in the plasma phase, that means they are distributed amongst large amount of energy, because as you know plasma is the fourth state of material at very high temperature. So, if you talk about your plasma television, inside there is gas in the plasma phase, and that is what gives you very high quality of picture. So, that is essentially the plasma is held together by the Coulomb interaction and Coulomb forces, which is essentially the long range interaction based on electrostatic attractive or repulsive forces. So, this is as we know from the Coulomb potential, Q I multiplied by Q j divided by d r, and d is the permittivity and r is the distance between the two ions. Then in this case it is an exponential decay. So, we are looking at that very simple, and then of course, the last one d is the potential which is short range, is 1 over r 12, which is the repulsive part of an empirical potential. So, now you know that as you can go out, there is no problem with some cohesive energy there, but as soon as you hit the wall, then you will have repulsion. So, it is mostly repulsive force here if you just do 1 over r. So, if you look at this, we come back to the Lennard-Jones, which is a pair potential, and we have looked at this picture many times, we understand that. Now, if you go to non-bonded, we know that there are two areas there in non-bonded. One is van der Waals, which we are looking into the van der Waals radii, at which point the electronic clouds start interacting with each other. That is the van der Waals radii, and for that we will have semi-empirical potential of Lennard-Jones, and then you could also have long range interaction where it is electrostatic. So, you are looking at the repulsion and cohesion. So, r over 12 right here, r over 6 right here, and then you are looking into long range, which is asymptotic to the 0 energy, and that is going into what we call as electrostatic regime. So, now we know what we have to do. This is simple van der Waals, which is r over 12 and r over 6, 1 over. So, now depending on different kinds of atoms or semi-empirical data, we can fit these informations A I k and C I k coefficients, we can come up with argon, krypton, xenon, you name it. So, this is a generic van der Waals model, and if you look at the Morse potential that we were looking at earlier, then like Lennard-Jones function, if you look at on your slide, we do have here eta, which is the potential energy, but now you are looking at r and r 0. So, we are looking at the equilibrium distance between the pair of atoms, and then we are looking at the exponential terms of that. So, if your repulsion force is more realistic, but attraction interaction is less so. So, you are looking at the two parts, repulsive, attractive, and the minimum neighbor position is at R 0, minimum energy zeta. Extra parameters A, which we are looking here, can be used to fit third property like lattice constant, bulk modulus, cohesive energy. So, now you see that how the empirical observations done by experiments are now going right into your equation. And that is the most important equation, because you will plug that information as the force field for the calculation of Newton's laws of motion. So, you can do F is equal to m a on one end, which is mass into acceleration using predictor corrector algorithm, but then on the other end, based on the position, you have to use this Morse potential or any one of the potential to calculate the force. So, this goes into calculation of that. Now, electrostatic we already understand, Q I, Q K, and those are the two atoms, and Coulomb is very long range potential. One of the big issues in the molecular dynamics simulation, by now you should realize, is the long range potential, because in the pair potential you can make that assumption that I will only look at the cutoff radius 2.5 sigma. So, I can go to 2.5 sigma is the lattice constant. So, let us say the lattice distance is 3.4 angstrom. So, 2.5 I can go to about 15 angstrom, and within that sphere of that radius 15 angstrom I will calculate all the pair potential, pair interaction. But when you talk about the electrostatic potential, then it is a long range. So, it does not cut off at 2.5 sigma radius, because there is it is a very long function with exponential. So, even at a large distances you can still feel some attractive or repulsive forces, and that is where they use advanced techniques like Ewald summation to make sure the charges end up correctly done, and positive charges, negative charges, they are all over the lattice space, they are distributed. And if you look at the reciprocal space in that lattice regime, then you can sum them up and the charges have to become 0 for a system to be inert or system to be electronically in equilibrium. However, if there is an ion, then there is a positive or negative charge. So, you also have to account for that. So, that is where electrostatic potential, although it looks very simple, is exponential decay with R. However, for calculating it as a electrostatic long range potential, there are a lot of things you have to do in your molecular dynamics code to make sure that the electrostatic forces are correctly accounted for. Another issue is that if electrostatic potential is there because of the ionic nature of system like sodium chloride, you put that in the water. Now, water has negative and positive ions, and so the water which was inert in terms of the motion of electricity through it, now is polarized due to NaCl. So, as you know, if you put salt in your water and then you put two wires, it will have a short circuit, while in pure water it may not happen, primarily because there are no charges there. So, I think these are the issues that you have to deal with in electrostatic potential. One of the big problem here is the pair potentials not always are good, especially with the structural or what we call as elastic property. So, one of the difficulties that you observe in pair potential, especially if you have liquid solid argon, or if you want to use these potential for metals, then it fails, primarily because if you look at the modulus of the elastic constant C12 and C44, which we will describe. C44 is shear modulus, and C12 C44 and C12 are two different elastic modulus that you are looking at, and the Cauchy relationship says that for metals C12 has to become C44. So, these different elastic constant have certain equality in case of metals. However, that does not apply, that does not work for metals. So, you cannot use pair potential model for metals. Also, pair potential gives outward surface relaxation, where low energy electron diffraction shows it as inward. So, if you look at a metal and then if you look at the surface, then you will see that the electrons, the atoms that are at the surface level, and so they have a bond length. So, the bond length decreases for the last layer, in case of the real observation based on the electron diffraction. However, if you look at if simulate them using pair potential, then they show expansion, because they are like springs. So, the springs have become free. So, this is not the real situation with the metals, and that is where we are now going to look at how we come over these kinds of problems in pair potential. Thank you.